Yeah, so today, what I want to do this morning is kind of dive a little bit deeper into Bayes. Yesterday afternoon, we kind of explained what Bayes was, talked about likelihoods, talked about the few cases where you could get analytical solutions to Bayesian problems, and that in practice, mostly we rely on numerical approaches, and then we talked about those conceptually, and then dove into an actual hands-on kind of leveraging JAGs or STAN to fit a very basic process model of a linear regression in either one of those two languages, JAGs or STAN. Actually, one thing that came up in conversation yesterday that I think is worth clarifying is that there is no such thing as Bayesian models. Bayes is a statistical approach for fitting models. The models are the same. So like, someone asked me, like, can you fit an ARIMA in Bayes? Like, an ARIMA is an ARIMA. That's a choice of a process model. You can fit that model in either a maximum likelihood or a Bayesian context. The process model is the same. The parameters are the same. Just now you have priors and you have a different set of numerical methods for fitting them. That said, Bayesian approaches do give us flexibility to relax a lot of the assumptions of classical models. And so what I wanted to do today is to dive into some of those assumptions. I'll start kind of thinking about this from a regression context, just because that's a common framework that's familiar to a lot of people, but it's everything I'm going to talk about here isn't restricted to regression. They're concepts that apply to pretty much any class of models. And I particularly wanted to kind of focus on a subset of things that are going to really help us in thinking about forecasting specifically. In the semester-long version of this, I go into kind of relaxing all of the assumptions of classical models, but here I'm going to focus on a few, particularly this idea of latent variables, things that we are interested in making inference on, even though we can't observe them directly. And two examples of that we're going to start with is the idea of errors in variables, which is the idea that maybe not all of the, if you think about a regression between some x and some y, maybe not all 100% of the error isn't just in the y direction. That there can also be uncertainty about the x's and missing data, which is a really common problem in pretty much everyone's data sets. Sensor went down, this team didn't collect that for some reason. I'm going to talk about hierarchical models, which allow us to kind of model the variability in parameters across space, time, or any other sort of measurement group, and then kind of finish up with a class of time series models called state space models that are particularly useful for forecasting. Like I said, a way of thinking about what I'm going to talk about here would be an example of a linear regression where there's a lot of assumptions that go into regression, and I'm going to kind of relax a couple of those. So like one of them is that assumption is that errors are additive and normally distributive. We talked a good bit yesterday about, you think about the data model that's appropriate to your data. There's scores and scores of probability distributions out there. So I'm not going to talk more about that today. In the interest of time, I'm not going to talk about relaxing the assumption of homoscedasticity, other than to say, if you think about something like a simple normal model, which has some mean and variance, we very often choose models that make this mean a function of something else. So a regression makes it a linear model of some x. A GAM makes it a spline model of something else. But there's absolutely nothing that says we can't do the same thing for the variance. You can write process models that describe how the variance changes as a function of space, time, covariates, etc. I'll just leave that as a concept without diving into the details. Observations are independent. We'll talk about a little bit that when we get to hierarchical models. Linearity, we kind of talked already a bit about. There's lots of other modeling approaches out there that relax that assumption. But here, I'm going to start with these two here. all the error is in the response variable. In other words, we somehow magically have observation errors in our y data, but measure our x's perfectly. That seems like a tenuous assumption. And that there's no missing data. And I'll say, ecological data and pretty much everyone else's data rarely conform to those classic assumptions. Before I dive into how to relax them, I want to introduce something that's very common in the Bayesian literature, which is some sort of graphical notation that allows you to think about how variables are related to each other without getting bogged down in the details of distributions and equations. So this is a graphical representation of a linear regression model. And what this says is that we have this data layer at the top where we have some x related to some y. We have some process model that has some parameters in it, some slope and intercept, and some sigma, some residual error. And that since these things are unknown and need to be estimated, we need to put priors on those. And so there's some distribution. So this might be some normal with some mean B0 and variance VB. This might be some gamma on that sigma. But rather than kind of getting bogged in the mouth, it allows you to think about things. A lot of people find this as an easier way to kind of think about how things are related to each other. And it's also going to be a framework I'm going to use to kind of graphically show how to relax some of these assumptions. So the first one I wanted to talk about is this idea of errors in variables. So our classic regression model is trying to minimize the residual error in this direction, the difference between some observation and some line. So regression models assume that all the error is in the y. But there's often non-negligible error in the measurement of any variable, so that's going to include any of our x's. So the idea of an errors in variables model is to put a process model on the x's as well. And that process model is, to start with, might be something very simple as saying, so the top line there is just our regression model. Our y's are normally distributed around some regression line, some covariates x and some betas and some sigma. But then let's think about that there's a distinction between what we're calling XO here, which is our observed x's, and what we're writing down there is just plain x, which is our what we'll call our latent or unobserved. Or, we'll call that latent. I'll put in quotes the idea of true x. So we never actually know what the true value of x is, but we know that the observed x is different from that true value by some amount. And one of the simplest possible models for that is what we've written there, that our observed x's are normally distributed around the true x with some. So this is now our observation error on x, as opposed to our sigma, which is our residual error on y. So when we do that, this latent x moves into the process model level. And so we have this relationship between the observed x and the latent x. We then use the latent x in the regression. So rather than using the observed x in the regression, we use the latent inferred x in the regression. There's this observation error tau, so we need to put priors on that. And the other thing we need to do, because these latent x's are unknown things we're trying to estimate, they all need priors as well. Which now gets us into a unintuitive thing that might make frequentists uncomfortable. So let's say I have n data points. I now need to, from n data points, I need to now estimate 2 betas, a sigma, a tau, and n x's. So I have to estimate more variables than I have data points, which seems impossible. But it's not impossible because you have prior information on these. That's not letting the x's wiggle that much, and also because one of the things the arrows show here is the way we gain information about the x's. So we gain information about the latent x not just from the observed x, but also from the y's. So the regression itself constrains not just what y can be, but also what x can be. So that's what this looks like conceptually. What this looks like in terms of implementation. So I left in black the things that we had in our regression model yesterday when we were playing with JAGs. So we had some set of priors on our betas and our sigmas. We had our process model estimating the predicted value of the mu for each data point. Observed y is normally attributed around that prediction with some sigma. But now what we're adding in is within this loop, within the kind of the likelihood loop, we've added this relationship between the observed and the latent x's. And then again, we're using those latent x's in the regression. We've put up there a prior on tau, and then we've set up a loop where we've put a prior on all of our x's. Here, I just set that to uniform 0 to 10 because I'm going to show you an example data set where I knew that all the x's are within that range. There's nothing magical about this choice, but I will say, and this is something that will come up as I dive more into latent variable problems, anytime you have a partitioning among multiple sources of uncertainty, and here we are doing that, we're partitioning the uncertainty in the x's and the uncertainty in the residuals. Anytime you have to do any sort of partitioning of uncertainty, the ability to use informative priors really helps. This is a place where if I have some way a priori to say what's the observation errors in those x's, to constrain that, or to constrain what the x's themselves can be, this will work out much more cleanly, because otherwise you can just kind of get trade-offs between the two. There's some amount of uncertainty, and tau and sigma are just kind of, if you make one bigger, you have to make the other smaller, and you kind of get one of these situations where you just kind of, your posteriors kind of look like that. They trade off with each other. It's hard to distinguish them. But there's lots of situations in the real world where you actually do have some ability to put constraints on these things. If I work with, if I'm working with someone else's derived data product, say something from NASA remote sensing, there often may be an error estimate that comes with that map. Or if I'm collecting field data where I'm counting something, there might be a natural counting distribution like a Poisson or a negative binomial that describes what that count data could have been. So it's not unreasonable to have informative priors on observation errors, particularly with sensor data because they come from calibrations, or lab data because you can have some sort of standards that you can calibrate what the range of uncertainty could have been in observations, which is actually very different than it's much harder to put a prior on the sigma because then you're asking, before I fit my model, I need to know how well it's doing. You rarely have priors on the residual error, but observation errors you often do. And in fact, it's not shown here, but if I have uncertainties in my x's that are actually varying data point by data point, I could actually put a different prior on every single x. So if I have a if I have a map that says the uncertainty at this location is 25 and the uncertainty in this location is 15, I could feed that into the Bayesian model data point by data point. So here's an example of applying this in practice. So this is the model I wrote earlier, where all my x's I knew were between 0 and 10. All my my y's are just scattered over there, and so I'm able to get a line fit through that data that makes sense. What I drew here were the posterior confidence intervals on each x and y. And an interesting thing that comes out of this that I think is worth noting, because when I've been talking about errors in x's and y's, there's inevitably someone in the audience that starts thinking he's talking about reduced major axis regression. And I will say, I am definitively not talking about reduced major axis regression, because reduced major axis regression is an approach that says rather than trying to minimize the error in the y direction, that's trying to minimize the distance perpendicular to the line between the observation and the line, which is a cool technique, but it's not the same thing as errors and variables, because you'll see is when I incorporate the error in each of the x's, these lines are still pretty much all vertical. Because if I have uncertainty in where x is, it's symmetric. It's just as likely to be in that direction as the other direction. We see some on the edges here. We do see some that are a bit diagonal, but most of them are pretty centered. There's no reason to say that, you know, when a point is above the line in the y direction, that all my residuals have to be in one direction. When it's below, all my residuals have to be in the other direction, which is kind of something reduced major axis kind of does. There's also the other thing that's notable about here is as you change this slope, you know, it kind of changes the uncertainties about these two things in a way that, I don't know, I don't think completely reflects the units of each of them potentially being different, or that we, like I said, that we may actually have prior information about what the range of observation uncertainty is. Another thing that's worth noting that's going to make all of you then groan and be like, why is he telling me this? I'll never do this, which is when you do this sort of analysis, it does make this confidence interval wider, because you now have two sources of uncertainty. So it means you have, you know, any sort of significance test will require a larger sample size. And so if I've just made your confidence intervals wider, you'd be like, why would you do that? That's not what I want. I want tight confidence intervals. And I would say what you want is honest confidence intervals. What you don't want is falsely overconfident intervals. And I'm going to jump to an example of that here, and I'll come back to this last slide. So here's an example of adding a little bit more complexity to that errors and variables model. So rather than just saying the observed x is, the true x is around the observed x, I might say the observed x might have, I'll make this, might have some linear relationship to the true x. And a common example of that would be any sort of calibration. So here I'm using as an example, I'm interested in the relationship between growth and moisture. This might be plants, it might be microbes, anything that needs moisture to grow. But the thing about soil moisture, if you don't measure it, if you're one of the epi folks, it seems like a simple concept. How wet is the soil? Well, the most rigorous way of measuring that is to pound a tube into the ground, pull the soil out, weigh it, dry it, weigh it again. Dead simple. But there's a limited number of times you can do that before you turn your plot into Swiss cheese. So, you know, if I want to measure soil moisture in real time, I need some sort of sensor. So I have some sort of, so TDR is one sensor approach. So I have some sensor, and then I need to calibrate that sensor against this Swiss cheese approach. And so I have some nice calibration curve. The R squared on that calibration curve is high. It's like 0.98 or something like that. You're like, calibration's great. I can ignore the uncertainty in that calibration because it's great. Well, just because it's great doesn't mean you can ignore the uncertainty. So here, what I do is I actually include the fitting of the calibration as part of the Bayesian model. And it's that calibration that gives me the relationship between what I observe from the sensor and the thing I'm trying to infer, in this case, soil moisture. Down in the bottom, I have an example of the thing I'm interested in predicting as a function of soil moisture. And in this case, it's a simulated data experiment, so I know what the true parameters are. So this black line is the true model. The black dots are simulated around that true model. And here's in blue is the model where I ignore the errors and variables and has a nice tight confidence interval. And the red is where I include that errors and variables. And yeah, you inflate the confidence interval, but you also don't miss the actual correct answer. So here, this blue version where I ignore the fact that there's this calibration relationship between the x's and the y's gives me a nice tight relationship that does not include the real relationship. So I'm confident, but I am falsely overconfident. So I think that, to me, that's a great example as to why you should be willing to pay the penalty of accounting for the uncertainties when they're present, is because, yeah, like this shows, yeah, and I'll say this lots this week, it's better to be uncertain, honestly uncertain, than falsely overconfident. A few other notes about errors and variables. They can have any functional relationship between the observed value and the latent variable. So here I have a linear calibration, but any sort of proxy relationship that may exist out there can be accounted for using an errors and variables approach. This thing's a proxy for that thing. It's calibrated. The calibration relationship doesn't need to be linear. It can be awfully noisy. These errors don't need to be normal. They don't need to be additive. You can count for known biases in those relationships. Like I said, they could be different types, like proxies. I also said this earlier, it's very useful to have informative priors where you can. So here's another example of an errors and variables model. Oh, did I not include it? Where was that? Maybe I didn't include it. I'll just tell you about it. So another example of an errors and variables model that is definitively, oh no, I included it in the state space. Mark recapture models are ones where all of your observed data are zeros and ones. I caught or I didn't catch the individual. But there's all this inference of latent states of, like, just because I didn't catch an individual doesn't mean it doesn't exist. So actually, I do have as an example, I have it later in the slide deck in a more complex model as an example of a decidedly non-Gaussian error distribution. It's literally just 0-1 data. Okay, so some more thoughts about latent variables as a concept. They are variables that are not directly observed. They're inferred from the model. So you need to put a prior on them. And both the data model and the process model provide constraints to those latent variables. Under the hood, what's happening is MCMC is integrating over all the values that those latent variables could take. So rather than imputing a single, like, gap-filled value for those things, it's literally as the MCMC is going through, it's sampling what those values could be. So thinking about what it's like, the simple regression example that I showed, like literally every time it alternates between like randomly drawing the redrawing the x's from their distributions and then fitting that regression using those now re-scrambled x's. So it's what's called a multiple imputation. So it's resampling those values continuously. They do contribute to uncertainties. And like I've said now many times, ignoring that variability could lead to falsely overconfident conclusions. So another example, very related example of latent variables is the idea of missing data. And you kind of think of this as the extreme case of the errors and variables model, where there's so much error in the x now that I don't even know what x is. So here I'm going to roll back the errors and variables assumption and go back to putting x in the data model, but I'm going to have this X in the missing part of the process model, and this is just making inferences about the subset of X values that are missing. So if I have, if only 5% of my data is missing, I only have, this X miss for that 5%. And then I need to put priors on those missing values. So here, when the data is completely missing, there's less constraint on this because you have the constraint from the prior, you have the constraint from your process model, but you don't have any, unlike the last example, we don't have the observed value as an additional constraint. So there will be much more uncertainty on missing data. But Bayesian techniques do provide you a way of formally accounting for the uncertainty in missing data. And where does this matter? So I find it matters a lot when you have multiple covariates. So if I just have I have one X and one Y, if some missing X and some missing Y, great, I just throw them out. All of us have always just thrown it out. But what happens when I have X1, X2, X3, X4, X5, and I have a few X1s missing, and I have a few X2s missing, and they're not all the same rows. And so I start throwing out whole rows of data because one thing is missing here or there. And if this hasn't happened to you, you haven't done enough data analysis yet. This happens to me all the time. And suddenly a data set that's like 5% missing here, 5% missing there, suddenly ends up like 50% missing, and you're throwing out like lots of places where you have I have 16 of the 17 covariates, and I'm missing this one. I have to throw out the whole round of data, and it gets really painful and it gets really wasteful because that data often costs you a lot of time and energy to collect. So missing data provides a way of kind of rescuing the other covariate data more than making inference about the one thing that you're missing. One key caveat in any missing data model is the data needs to be missing at random. And there's a formal statistical definition of what missing at random means, but it's kind of intuitive. Like if there's any systematic pattern to the missingness of the data, you can't impute it. So if I'm working, and so one of our examples is an aquatic example. If I have sensors along a depth gradient and the one at the bottom of the lake goes out, I can't use the data from the top of the lake to impute what's happening in the bottom lake because it's going to be systematically different. But if I just have random sensor glitches through time, that's random. Another great example, I work with a lot of what's called eddy covariance data, which is a way of making measurements between the land of carbon fluxes between the land and the atmosphere. It tends not to work well at night because the atmosphere tends to be very still, so there's no movement of the air to measure. So that violates the assumption of missing at random because the data is missing systematically at night. But now remember, we have this idea of conditional probability. Conditional on time of day, that data may be missing at random, because whether it's missing Tuesday or Thursday or Saturday may now be completely random, conditional on the time of day. So missing at random can be conditionally missing, but there can't be a systematic pattern to it, because then you're trying to use the data you do have to infer something that may be out of sample. Implementing missing data models in JAGs is actually dead simple because of a wonderful feature of JAGs, which is if something is missing. So I never really talked about this yesterday, but if I wrote a JAGs model that said y is normal, if the y is provided, JAGS says, oh, you must be trying to make inference about what these two parameters are. If y is not provided, it's saying, oh, you must be trying to draw a random number for what y must be. You must be trying to simulate y. And that actually makes it really easy to implement these missing data models, because all I need to do is put a prior on the missing data model. There's nothing I need to do special in the likelihood, because there's just nothing there's nothing special here. Literally, all I need to do is put a prior on the missing values. And here, this is just a vector of which values are missing. So here I might have some set of x's and y's. This one is missing. I put an NA on it. I put a prior on it, and yeah, Jags is happy to then give me a posterior for what that x could be. And so here's an example with that data set I had in the last slide, where I've now drawn in the posterior distribution for what, here's the y value, it was at 7.5. Here's my posterior for what that x could have been, and we can see, I started with a uniform prior on what it could be, but it's now constrained to be like, okay, we're pretty sure it was over in this part, which is because it's really gaining the information from the y through the regression on what that x could have been. And again, if all I have is just one x and one y, like, because the y is telling me what the x's could be, that x isn't really telling me anything about the regression. It's really more powerful when you have multiple x's and multiple y's, or when you're trying to do some sort of inversion, when you're trying to go from y to infer what x could have been, which is essentially equivalent to a missing data model. So yeah, so these values are more likely, those are less likely. Okay. How's everyone doing? Questions? So I think, like most things in Bayes, the theoretical answer is no, the practical answer is not no. Theoretically, you could fit a regression between x's and y's with no observed x's at all and just missing data on all of them, but your only information about the x's would then be your priors. And if your priors are uninformative, all it's going to tell you is you're going to get a regression back, and it's going to say there's no relationship between x and y because you're not telling us anything about what the x's are. The other thing that happens as a practical basis is within MCMC, anytime you have latent variables, there's something that it needs to keep track of. And so you can run into memory issues. So if I have a million latent variables to keep track of times 10,000 MCMC steps, that's a 1,000,000 by 10,000 matrix that I now need to store in memory to get the posterior output. So that's really the more practical thing that I find happens more often. So we did a paper looking at trait databases where we're trying to understand the covariances, and that's a place where there's tons of missingness. You'll have this pair of data here, that pair of data there, but like no one ever measures all possible traits for every species. So it's a big missing data problem. That was an example where Stan in particular really struggled because of the amount of missingness. Jags was able to give us an answer, but yeah, I mean but I think in essence we ended up telling Jags not to bother to give us the posteriors for all the missing data. We really just wanted to make inference on the parameters. So yeah, it kept track of it internally in memory, but it forgot the values immediately. Cool. So next I want to talk about one of my favorite concepts in Bayes. It's the idea of hierarchical models. And I'm going to describe hierarchical models as a continuum of middle values between two possible n members. So think about some data that I'm collecting over multiple sites. You can substitute site for any sort of measurement unit you're interested in. It could be years, people, individual organisms you've tracked and colored. Like they're just some measurement unit. And usually I've replication within that measurement unit, which is actually worth mentioning. So I might, here I have 3 sites. I have at one n member the option of fitting my model to each of those 3 sites independently. That now assumes that there's no shared information between those sites. each of them is independent. I'm not really leveraging any sort of shared information that they might have. But in reality, you might be like, well, I mean, all these are all pretty similar. I expect these relationships to be similar. You know, maybe I want to share information. So at the other extreme, I might fit one model across all of my data sets. So I've pooled my data, which is great. Now I'm borrowing strength across all of my data set. But now I'm treating all of these different blocks as if they are actually identical, which ignores the fact that like replicates within this site are probably more likely to be like each other than the ones within there, so that they're, if these are in space, there's this, basic principle of geography, things that are closer together are likely to be more similar. These observations are not independent of each other if they're all coming from the same plot. So I've kind of ignored that here, but I've thrown away any shared information there. So hierarchical models represent the middle ground, which is to say, I'm going to fit a model where I fit each model to each data set, but then I'm going to fit another model at the hierarchical level that describes how the parameters vary from site to site. So if mu here is just something as simple as fitting a mean, I might fit a mean to each data set. I might fit an overall mean, or I might do here, I fit a mean to each data set, but then I fit this higher level model that says, but there's some global mean across data sets and some site to site variability of how different the sites are from each other. So I'm no longer, once I add that hierarchical level, I'm no longer treating the sites as independent because there's shared information across them and some explicit accounting of across-site variability. A key part here, though, is that this is being fit all at once. So it's not like I'm doing this, and then once I have the posteriors for these, then fitting another model on top of that. If I did that, I wouldn't really be sharing information. I would just be estimating the across-site variability post hoc. By fitting them simultaneously, I kind of essentially say, up there I have this mu, which ends up being the prior for each of these, and it ends up being informed by all the other mu's. So I'm essentially adding another layer because I'm now letting the priors be informed by all the other data, but then I need to put a prior on that because it's now an unknown parameter. So I've left all the priors off of this. Does that make any sense? I don't know if I did a great job of explaining that. So this is what this looks like graphically. I have some data modeled out there. I've now substituted x's for y's. And each of those aren't individual data points, but they would be like a vector of data within each measurement unit. So those might be observations over time within a plot, or observations of different individuals within a plot, or other measurement unit. I'm fitting my process model to there, where I have a model for each. And then I have this across-site model here where I have, if this is just a simple mean, this would be a global mean, and now my estimate of the cross-site variance. So I have this. So I talked about this idea of partitioning uncertainty earlier between x's and y's. Now I'm partitioning the uncertainty to a cross measurement unit versus that sigma, which is your within measurement unit variability. So we have that sigma at the lowest level telling us how the y's differ from the mu's. And then we have this tau here telling us of how the mu's differ from each other. Cool, and then I have priors on each of these. A couple things that I think are worth noting about some of the strengths of hierarchical models. One of the key strengths is this idea of borrowing strength, that you're leveraging information from the different measurement units to that come up to inform this prior, and then kind of trickle back down to inform the estimates in each of those units. You've now kind of, you've both accounted for the non-independence within the measurement units and kind of leveraged information. It's worth noting there is no assumption in hierarchical models that those data sets are balanced either, which is actually where they can be particularly powerful. So if I have lots of data on some of my sites and limited data on the others, the sites with limited data, well, the sites with lots of data, kind of overwhelm their prior. They do what they're going to do because they have lots of data. The sites with very little data, they benefit a lot from learning about what's happening at the other sites, because this informative prior is a strong constraint at those unmeasured sites. It's also really important for prediction. So it's worth noting, what happens if I have X4? Suddenly there's some new site that I want to make a prediction to. If I fit each of these models independently, how do I predict to X4? I can't. There's no statistical basis for predicting out of sample if you do this, because you've assumed that every site is completely independent. If every site is completely independent, you have no information. That these three models aren't helpful at all for predicting the next site. Here you can predict the next site, but your prediction to an out of sample location is going to be just as confident as a prediction to an in-sample location, because you're saying all sites are identical. So if I have a new X4, the confidence interval in that new X4 is going to be exactly the same, and that seems wrong. If I'm predicting to a new site, I should be more uncertain than if I'm inferring what happened in the sites where I have lots of data. Hierarchical models actually solve that problem too, because if I have some fourth site here that I'm trying to predict to, I can use this hierarchical model to predict mu4, because I'm drawing it from that hierarchical distribution. So if I want to predict to some new n, I'm essentially sampling from this distribution to predict what that mu should be, and then sampling from the sigma to predict that variance. So you're going to have this very natural behavior where out of sample predictions to new sites will be more uncertain than in sample predictions. And it gives you a formal way of actually making out of sample predictions. Cool. So this is kind of a standard hierarchical model, and there technically you can have multiple levels of hierarchy as well to deal with multiple sources of uncertainty. But they can get really messy really quickly. So there's another way that these models are often rewritten. So I can take that hierarchical model that I just wrote and rewrite it this way, that now says, instead of each site having its own, mu1, mu2, mu3, mu4, distributed around a global mean, I can instead say each data set has a global mean plus alpha, a site-specific deviation. So now I'm essentially just recoding the alphas as being how far each site differs from the global mean. These are now, by definition, centered around 0, because they're centered around that global value. So this is just the site-to-site deviations. That formulation makes this very analogous to the concept of random effects in frequentist models, where you can have an effect on how each parameter differs. But I think an important thing to note about hierarchical models is that here I've written the random effect as an additive deviation from this parameter. The deviations could be on any parameter in your model. They don't just have, so in traditional random effects models, so I'll step back and say the kind of, if I wrote a model, normal mu plus some random effects, that would be a random effects model. If I replace this mu with some set of covariates, that becomes a mixed effects model, because I have a random effect and then I have some known covariates called fixed effects. And I can have, the nice thing about rewriting things as deviations is that instead of, if you have multiple sources of uncertainty, instead of stacking them up vertically as hierarchical levels, you can just write down different effects. Like I might have a random effect of time, a random effect of site. I'll actually use X for site. I could also have like a random effect for species. If I think if I'm working in a system that has multiple species and I think there's some shared information across them. But I can also say, write a model that might say, put a random effect on my regression parameters as well. And mixed effects models let you do that in traditional regression as well. But where it gets more complicated is if, let's say I have some stock recruitment model that's some nonlinear function with some other set of parameters. I can put random effects on any of the parameters in that nonlinear model as well. So the idea isn't limited to linear models. The idea is that you can actually measure you can model the variability in any of your parameters, in any model, in an SIR model, stock recruitment model, biogeochemical model. I can model how the parameters in that model vary through time, vary through space, vary by species, anything that I want to share information on. I can use this formulation to model the variability in the parameters. Other thing worth noting, this is a more advanced topic. That variability doesn't need to be independent. So right here, I'm modeling this as a univariate normal around some tau, thinking about every deviation being independent. If you start getting into spatiotemporal models, which is a more advanced concept, you can account for the autocorrelation in those random effects fairly straightforward way. If you know anything about spatial stats, you can essentially, or time series, you could fit a year effect where the year effects aren't independent from time but are autocorrelated. You could fit a spatial effect where the random effects aren't independent but are spatially autocorrelated. I won't go into how you do that, but I'm just letting you know that in concept, you can make these random effects correlated in space, in time, phylogenetically, however you want to account for their non-independence. They don't have to be assumed to be independent. What they have to be assumed is to be mean zero and deviations from what your global parameter is. Anyone have brain cells left? I'm trying to blow minds here in terms of what you can actually do in these frameworks. Yeah. Yeah, I mean, in this case, a random intercept is no different than just putting them additively on the end. If I had put it like around beta 0, it's equivalent. Yeah, I mean, a random intercept model is easiest thing to implement, but all it does means is that like your intercepts are different. But your slopes might be different, or your model might be way more complicated than a straight line. And your other, so we have a model, we have a preprint right now, it's not been published yet, where we take a terrestrial carbon cycle model with 20 parameters per plant functional type and fit it hierarchically across a whole network of monitoring stations, and actually then allows us to understand in this complex biogeochemical model like how the parameters are actually varying from site to site, which is really cool because it, one of the things that's a challenge with models when they get complex is trying to figure out like how to fix the next, how to fix them when they don't fail. So the hierarchical model, instead of the traditional way that we improve process-based models is we add something to it that we think matters and then see if it improved things or not. This often leads to model creep, which is once you've added something to the model, you never take it out again, even if it didn't matter. Because you can always argue that it does. The hierarchical models actually now let you say, well, where is the important unexplained variability? So we're able to see like, oh, this parameter that controls soil respiration, it varies from site to site, along a latitudinal gradient that sure seems to be explained by like, ecotypic acclimation. Like, so we could say, like, we could actually figure out like first what processes were missing from the model, and also because we have this estimate of a cross-site variability, what the relative importance of those things were. Which things were really variable from site to site and which weren't. Which actually was, this is an idea. So another key idea here is that hierarchical models let us account for sources of variability that we observe that are persistent, but we can't yet explain what's causing them. Doesn't mean that you shouldn't try to explain what's causing them. This figure shows another point about hierarchical models and kind of the impact of partitioning uncertainty on inferences and forecasts. So here are 10 time series over 10 points in time. And in this top example, there's a lot of, I think something like 75% of the variability is site to site, and 25% of it is through time, and the other, it's the opposite. Most of the variability is through time, and 25% of it is site to site. So let's say in this case is an example of what if for each of these two cases, I want to make a prediction to a new year for a known site. So in this one, if I want to predict a known site into a new year, I'm actually quite tight around that prediction because I know I've partitioned those sources of uncertainty. Here, a new site, a new year for a known site is very uncertain because most of the variables site to site. This other example is making a prediction for year 10 at a new site, and I kind of get the opposite. So even though the total variance in this data set is the same, there's no covariates, there's just random effects, I actually make very different predictions for these two cases because of how I've partitioned the uncertainty. So in both cases, making a prediction to a new site and a new year is essentially identical because you can't leverage that partitioning of uncertainty when both the site and year are new. Okay, so some things, I've said a lot of this already, but random effects attempt to account for the unexplained variance across some group, plot year, et cetera, blah, 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 due to all the things that were not measured. The not measured is worth noting. Like if you have explanatory covariates, you should use them and see if they are significant, not just as, random effects hierarchical models are to explain the variability that you can't explain with the known factors. They may point to things that need additional explanation. Adding covariates may explain some portion of that variation, but there's always something you didn't measure. So the x's may increase, but that doesn't mean the random effects go away. Sometimes additional fixed effects are not justified. So sometimes I know an x that matters, but model selection says that I'm actually better off just treating that as random because it's contributing so little to the model that the uncertainty that's introducing is greater than the variability it's trying to explain. Okay, I am bad on time. So I'm going to apologize. I'm going to go a little over, but I'm going to try to go through this quickly also. So I want to talk about dynamic models next. We've talked a lot about kind of thinking about regression, but a lot of forecasting uses time series models that have this dynamic formulation. I'm predicting some x at some future point in time as a function of x right now, plus some covariates given some parameters and some process error. So this is like all population models have this formulation. You know, the population in the future depends on the population right now. Your SAR models have this formulation. Biogeochemical models have this formulation. It's very common across ecology to say I'm trying to predict something where the state of the system right now is one of the things I use to predict the state of the system one time step into the future. So I have some state variable x, some covariates, some parameters, some process error. So here's an example. State models are for when you, oh, didn't jump ahead. That's weird. Ah! Zoom is disconnected my slides. I was advancing slides and then realized that you guys weren't seeing what I was showing. Okay. Yeah, those things. So state space models are when the y you observe is different than the latent variable you're trying to make inference for. So you have water samples in test tubes in the lab that you're analyzing, but you want to observe the actual state of the system. So there's some different, essentially state space models are when you want to do time series and you have errors and variables problems. So they have this basic framework where I think about, I have some observed state of the system y, and here these x's and y's are not like regression as much. So actually, what I'm calling y here is essentially what I was calling xo observed earlier. So the observed version of the state of the system. So the observed state of the system versus the latent state of the system. So I have some, essentially errors and variables model connecting the latent state to the observation with some observation error tau. And then I have, separate from this, some process model that's connecting to how the true latent state of the system is evolving through time. And then there's some, what I'm calling tau add here. I did it because it's additive, but often it's better to more think about that other as being the process error. There's some error in the process that propagates forward in time. Either of these relationships can be arbitrary functions. So, we might start with, these y's just being normally around these x's for a simple observation error model. But we already talked about in errors and variables, you can make those arbitrary, deal with calibration, deal with proxy variables, et cetera. And then we have this latent variable, which is our dynamic process. So we have a process model that is itself dynamic. It has this property of the future as a function of the present. And it can be any arbitrary function. But what we've achieved here is a partitioning of uncertainty between observation error and process error. And one of the reasons we do that is because, I'll talk more about error propagation this afternoon, process error, the fact that our model is never perfect, affects our predictions into the future. Observation error doesn't. Our inability to measure the system perfectly doesn't change the state of the system. So here's a simple example of a state space model that is just a random walk, where I'm just saying x in the future is normally distributed on x right now plus some process error. So there's no mechanism. It's literally xt plus 1 equals xt plus some error. This is also sometimes called the persistence model, and it's a really useful null model. Tomorrow is the same as today, plus some noise. To show you the power of the state space model, you can ask the question of, what affects my ability to estimate that latent x? And this is actually easier to observe, to figure out if you look at this in the graphical form. I have some latent x here. These 4 red arrows all contribute, as well as the prior, contribute to my ability to make inferences for that x. So it depends on the x before it, depends on the x after it, and it depends on the observations. So the conditional distribution of x depends on all of those 3 things. So I've written down the process model, the observation model, and I've just put, these are just priors on everything else. Prior in the observation error, prior in the additive process error, and the other thing worth noting, I need to put a prior on the initial condition. So the first x at time 0 also needs a prior. All the other x's don't need a prior because they are informed by the x before and after it. There's cool special cases here. So if you're at the first data point, you replace this line with the prior. If you're at the last data point, you just don't have constraint on the future. Your constraint on x comes from the past and the present. If you forecast off the front, essentially the last case is like forecasting off the front. Your constraint on the next x into the future just depends on the x before it, because there's no x in the future and there's no observation at that point in time. If I have missing data, my constraint on x comes from the x before it and the x after it. So one of the advantages of state space models is they are remarkably resilient to missing data, and most time series methods are not. Most time series methods really hate gaps. Most time series have gaps. So here's an example of, here's this flu index through time, the full data series. Here I made these x values missing, and we can see when it gets the missing data, it's happy to make inference about it, but the confidence intervals get wider, and the confidence intervals have this kind of classic, I kind of think of it as like this balloon animal shape or this American football shape, where the uncertainty increases as you get away from the last observation, and then decrease again as you get closer to the next observation, because I have constraint from that future observation. This is just the JAGS code to actually implement a random walk model. I'll post all this so you can see it later. And now forecasting in a state space model can be as easy as setting the future to NA. Because remember, if you set something to NA, JAGS is happy to make predictions of it. It's just missing data. So similar to a gap, so in a gap, you kind of get this balloon animal shape because you have constraint from the future. In the forecast, you don't. It just only has constraints from the past. So the uncertainty will increase as we go out into the future. And this is kind of this point about this importance of partitioning the process error because it propagates in time versus the observation error that doesn't. So when I predict off the future, I'm not inflating that by the observation error. This just shows that I can take that random walk model and modify it to add some real process. In this case, I've just added a logistic growth model up there as my process model, and then I've put priors on R and K. And kind of contrasting the inference we get from fitting a time series, in this case, this is moose data from Poland, fitting a time series where we treat this as a process with observation error versus where we treat this as a function. So that, like that, if you took a logistic growth model and just fit that as a sigmoidal shaped function where you're trying to minimize error, you get that fit. And this is where you try to fit this as a process, where you say from time point to the next, I have this concept of density-dependent growth that's constraining my understanding, but I also have data and process error that acknowledges that my process is itself imperfect. I don't know about you, but I'd rather predict the future using this. So generality, X and Y don't need to be normal. They don't need to be the same type of data. They don't have to have the same time scale. It handles missing data and irregularly spaced data easily. So, if the measurement frequency isn't fixed, state-space model doesn't care. Multiple sources of data. So if I have, one type of observation, if I have multiple types of observations, I can fuse them within state-space models because each of them just they have the same latent X, but they have different observation error models. And you can handle time, I won't go into how you do this, but you can handle time integrated observations as well by just relating, say, the mean or sum of multiple latent X's to one observed Y. So this is where I talk about the Mark recapture as an example of a state-space model where the process model follows a Bernoulli distribution, a 0-1 coin flip distribution, and the observation error model follows a 0-1 coin flip distribution. Same framework, completely different data models. Also worth noting that state-space models don't just have to be used for time, they can also be used for space. So state-space models used for a raster go by the name of a Markov random field. When they're applied to vector spatial data, they're called conditional autoregressive model, and they provide an alternative to kind of traditional geostatistical models, similar to how the state-space model provides an alternative to like traditional ARIMA models. Okay, apologies for eating up too much of your break. I just got too excited in the middle there. Thanks.